we will show that the language that is a set of strings M1, M2, such that M1 and M2 are Turing machines, and the size of the intersection of the languages of M1 and M2 is greater than 5 is undecidable. So what we're saying here is that M1 and M2 have more than 5 strings in common. Okay, so remember with undecidability, we generally want to do a reduction. So here we're going to do a proof by reduction from ATM. We're going to obtain a contradiction. In general, we can just do a reduction from any undecidable language and show that if there is a solution to this new language, then there would be a solution to the undecidable language. So therefore, the new language cannot be decidable. Okay, that's the structure. So here's our proof. Assume to the contrary that L is decidable. Okay, therefore it has a decider, and we're going to let D sub L be the decider for L. Okay, so we're going to use DL to construct a decider DTM that will decide ATM. Okay, and our idea here is going to be to construct a machine that accepts sigma star if and only if M accepts W. Okay, then we're going to feed 2 copies of the machine to DL. Since both copies accept the same language, and the language is infinite, right, it's going to accept sigma star if and only if M accepts W. Then their intersection is going to be greater than 5 if and only if M accepts W. Okay, so let's see, let's construct a decider DTM as follows. Okay, so what does DTM do? Yeah, I think I can fit this on the same page. Okay, it's going to take an input, okay, MW, right, because DTM is going to be our decider for ATM, so its input should match what we would expect for ATM. Okay, so number 1, we're going to use the description of M along with the string W to construct a new machine, which we're going to name M prime W. Okay, so this machine is going to be very specific to M and W. All right, what does this new machine do? M prime W. Oops. We're not quite in the description yet. Okay, what does it do? On any input, so on input X, it is going to, let's number this A, simulate M on W. Okay, so I said M prime W is going to be very specific to MW because it takes, we're going to use the description of MW to construct M prime W, so it's going to simulate M on W and accept X if M accepts W. Okay, so if M accepts W, this new machine would accept every string. Okay, if M does not accept W, it can't accept, so then its language would be empty. Okay, notice this machine is inherently a recognizer because M may run forever on W, so then this machine would run forever on W. Okay, however, this doesn't matter because we aren't actually ever going to run M prime W. Okay, we are going to feed its description to another machine, right? So what is that machine going to do? Okay, so after we've constructed this M prime W, we're going to run DL, our decider for language L, on 2 copies of our newly created machine. Okay? And we're going to output whatever DL outputs. Okay, this is the same thing as saying if DL accepts, accept, if DL rejects, rejects. Okay, it's going to do whatever DL did. So notice here, we're assuming the existence of DL and we're assuming it's a decider. We don't know how it operates, but all we need to do is feed the 2 descriptions into DL and it's going to give us a decision. All right, what decision is that? It's going to accept if the intersection of these 2, the languages of these 2 machines is greater than 5. Notice it's the same machine. Okay, that's going to be really important. Okay, so now we would want to explain why is DTM a decider for ATM. Okay, and let's consider what would happen if we take an arbitrary string in the language of ATM. Okay, so if MW is a string in the language ATM, what happens? This is going to imply that M will accept W by definition of ATM. Okay, then what happens? When we construct M prime W, if M accepts W, M prime W accepts everything. Okay, so then the language of M prime W is sigma star. It's every string over the alphabet. Okay, what does that mean? It means that the size of the intersection of that language with itself, okay, so the intersection of a language with itself will always be the size of the language originally, right? So the size of this intersection is infinity, right? This is an infinite language because it accepts sigma star. Sigma star is infinite. Okay, that's definitely bigger than 5. Okay, and then DL accepts, to put it down here, M prime W, M prime W. Okay, what happened when DL accepted? Well, then DTM accepted. We did whatever DL did. Then DTM accepts. Okay, so take an arbitrary string in the language of ATM, DTM is going to accept it. What happens if we take an arbitrary string that's not in the language? Okay, so the string is not an ATM. Doesn't accept W. Remember, when M doesn't accept W, M prime W won't be able to accept anything. It can only accept when M accepts W, which means that the language of M prime W is the empty language. Okay, what's the size of the empty language? 0. Then what's the size of that language intersected with itself? 0. Okay, 0 is, in this case, less than or equal to 5. Okay, which means that our decider for language L is going to reject. Okay, again, we're assuming the existence of DL, we're assuming it's a decider, and we are assuming that it decides the language L. Okay, so this string, where the intersection, the size of the intersection of these 2 languages, if it's less than or equal to 5, then DL is going to reject it. It's not in its language. Okay, so then DL rejects, this input. Okay, and what happens when DL rejects? DTM rejects. It does whatever DL did. So DTM rejects. Okay, so if the string is not an ATM, DTM is going to reject it. Therefore, DTM is a decider for ATM, which implies that ATM is decidable, which is where we get our contradiction. Okay, where did our contradiction come from? The only thing that we assumed was that L is decidable. There's our contradiction. L is not decidable.